In this third and final component of the theory lecture on laminar flat plate boundary layers, we are going to do some analysis of the boundary layer in terms of the governing equations. So I'll show you a little bit of a derivation of mass conservation, and then we'll talk about what the momentum conservation equations look like. And these are essentially going to be the equations that are solved by the solver in SolidWorks, because we're only going to be considering terms that are actually varying appreciably in this context. And so we'll see how we can kind of do what's called scale analysis of the equations to understand how the boundary layer is going to grow. And it's a really simple piece of mathematics that's also very powerful. And you use it quite often in the analysis of fluid flows. And so we're going to see, for that reason, how it applies in this circumstance and what it might tell us about the flow we're looking at. So 100%, there we go. So to begin, we're going to take this boundary layer. So we've got delta of x, and we want to look at a fluid element. So this is a fluid element. And to start, now we've got kind of flow going in and out. In the last lecture, we looked at a 1D mass conservation. Now we will see a 2D mass conservation. So we have m dot in x, m dot out x. But we also have mass coming in and out vertically. So we have m dot in y and m dot out y. And so for the mass balance, we want to specify all of these terms and then add them all up and say that all of this has to balance out, and it should all be zero. And so now you're getting a sense that, well, in 3D, you would just add another dimension. And that's really the first step to constructing the Navier-Stokes equations. And the fully fledged Navier-Stokes equations are really the basis of modeling fluid flow for most cases. Not always, but in most cases, when you do CFD, you're solving the Navier-Stokes equations. So from this diagram, we can write out explicit form of all of these. So we have m in x. That's going to be equal to, let's just note that we're dx and dy, right? So we've got this little box that has a length dx and a height dy. So here we have rho u dy. That's what's coming in. And m out x is going to be equal to rho u plus du dx times dx dy, right? So we have du dx is changing over dx, and then you multiply it by dx, and that will give you the resultant flow. And we have m dot, flow speed, I should say, in the x direction. We have m in y, which is equal to rho v dx, and we have mass flow out in the y direction, which is equal to rho v plus dv du, sorry, dv dy dv times dx. So we can add these together. We know that ins have to equal outs. So we can say rho u dy plus rho v dx is equal to rho u plus du dx dx dy plus rho times v plus dv dy dy dx. Okay, oops, that didn't work. Okay, so why do we do this? We'll first notice that when we pull the dy's in, these terms are going to cancel with the first term, right? When you pull the dy in, dx in, those are going to go away. We can also get rid of all of our terms for density. And when we do that, what we'll be left with is we're going to have du dx times dx dy plus dv dy times dx dy as well, which is like a differential area of this little fluid element equals to 0. Alternatively, we can write this more succinctly by dividing out by that area, and we can say that we have du dx plus dv dy is equal to 0. That is mass conservation. And so when you do momentum conservation, you do the exact same thing where you're looking at rho times u squared dy. So you've got momentums coming in. You're going to have a pressure. You have a pressure coming in and you have pressure pushing against the flow in the reverse direction. And you're going to have shear stresses. And when you add all of those up, which you can email me and ask about it, and we can go through that derivation if you're interested. But as before, I'm just going to show you what that equation looks like. So here we have mass conservation. And your final x direction momentum conservation is going to be u du dy plus u du dx plus v du dy equals -1 over rho dp dx plus nu d squared u dy squared. Okay, so this is x direction momentum. And like I said, you can derive it by just applying a force balance to this fluid element. And I'm happy to go through that with anyone who wants to see it. So x direction momentum. And in the y direction momentum, what we're going to have is dp dy equals 0. So much more simple. And we can make some of these simplifications that you'll see here, like the full 2D equations are actually longer than what I've written for that x direction momentum, and of course longer than this in the y direction momentum. And that's because these are simplified to the general case of a boundary layer. Their pressure terms in here will go away, as we will see shortly. But the point of doing this, the point of retaining the pressure terms is that you might have an adverse pressure gradient or a favorable pressure gradient. And we're going to encounter situations like that later in the class. So I'm leaving P in, but these equations have been simplified for 2D boundary layer. So here, this is y direction momentum. And when we take all of these equations, this is essentially what's going to be solved by SolidWorks when you're running your flat plate boundary layer analysis. And that's because the additional terms that you're looking at, this is in the laminar case, I should say, the additional terms that you're going to look at are, when you have the full Navier-Stokes equations, are not relevant if you have a steady laminar boundary layer. Okay, those terms do not appreciably affect the variation in your flow profile. Everything that's being done in SolidWorks, even though it might solve all of the equations, these are sufficient to describe the scenario. So we're going to do some analysis of these equations. And what you would really do if you wanted to get profiles for delta, the numbers that you get in the previous lectures, those correlations, come from an analytical solution in the laminar case, and it's called the Blasius solution. And I can describe it. I'll write it down for those of you who would like to see. It's another thing we can go through together if you want, but it's a little bit outside the scope of this class. But you can solve these equations exactly with the Blasius solution. And what you do is you start off with a hypothesis. You say, well, as we go along in that flow field, you know, the boundary layers should basically look the same. Let's get rid of that. So we should have boundary layers that look kind of the same. They're just getting bigger. So they're kind of getting stretched out with the boundary layer. So if we assume that we have a velocity profile that can be written as a function of the boundary layer times a profile that's the same everywhere in the flow that just stretches to the height of the boundary layer, then you can transform these partial differential equations into ordinary differential equations, and you could get a nice, simple analytical solution that gives you a function for u as a function of x and y throughout your whole flow field. What we're going to do is skip over that solution and do a much simpler thing called scale analysis. And this comes up all the time in fluid flow, because often we just want to see how the magnitudes of things are going to change. The very precise multi-decimal place solution might not have much more utility to us than an order of magnitude solution. So we'll introduce some scales. And for instance, we'll introduce u prime variable, which is going to be the velocity in the x direction normalized by the x direction velocity scale. So u prime is going to be equal to u over u infinity, such that u is equal to u prime times u infinity. So in this case, u infinity is the scale. We'll have the same for v prime, x prime, and y prime. So we want these kind of variables that have been scaled in each case. So v prime is going to be v over vs, and we don't know what the scale is for the velocity in the v direction yet. X prime is going to be x over the length of the plate, and y prime is going to be y over delta, the thickness of the boundary layer. So of course we can write v, x, and y as a function of these. So we have v equals v prime times vs, which is as of yet unknown. X is equal to x prime times L, and y is equal to y prime times delta. Now, if we go back to that mass conservation equation, di u di x plus di v di y equals 0, what we can do is we can say, so let's write it out, du dx plus dv dy equals to 0. Now, what we want to be able to do is sub in these profiles. So we could say du dx is equal to du prime u infinity times d x prime L. And of course, u infinity and L are constants. So this is equal to u infinity over L times di u prime over di x prime. And that is what we'd like to do to all of the terms here. So this is equivalent to saying u infinity over L times the u prime dx prime plus, vs over delta times dv prime dy prime equals to 0. And now what we'll notice is that these terms should all be of order 1, because we're trying to select scales that have that property. So we want scales where x is never going to be like way larger than 1. It's not going to be 10 or something like that. And that will just allow us, if we select the scales properly, so that that property is satisfied, so that this is of order 1, and this is of order 1, because v prime and x prime and u prime and y prime should all be of order 1. They should be around 1, not 10 times larger than 1. And if we do that properly, then we can make rough statements about the size of the other scales with respect to each other, as long as those scales have been selected well. So in this case, we can say that u infinity over L times du prime dx prime is equal to negative vs over delta times dv prime over dy prime. Now, the left and right-hand side of this equation, they have to be equal, but it's not necessarily equal to 1. What is equal to 1 is these values inside the brackets. Those are approximately 1, like we've been saying. So then any difference between those values and 1 on the whole left and right-hand side of the equation is going to be from these constants. So we can say that the velocity in the y direction over delta is on the order of u infinity over L. And of course, we can multiply both sides by velocity. So we get that the velocity is going to be proportional to, not proportional to, but of the order of u infinity delta over L. So that's pretty cool. Just by analyzing the fact that we're going to have to conserve mass in a random fluid element, we can say something about how the velocity in the y direction is related to different scales of the flow. And that's important because, well, in this case, this is going to be instrumental. We don't necessarily directly care about the velocity in the y direction. It is interesting, though, because you have at the start only velocity in the x direction. And now because we're slowing the flow down, we have to have velocity components pushing upwards. And we can say approximately the speed of those with respect to the size of the problem that we're looking at. So if we go to the momentum equation, we can do the same thing. So I'll restate the equation. We have u du dx plus v du dy is equal to -1 over rho dp dx plus nu squared du d squared u dy squared. Okay, and in the context of our boundary, this is going to be 0 because the u infinity is not speeding up or slowing down. It is staying the same everywhere. And so that might be unintuitive, but if the flow isn't speeding up or slowing down, then you're going to have a pressure gradient that the pressure gradient is not going to exist because pressure would exert a force on the flow. So if you had a positive or negative pressure gradient, that should either accelerate or decelerate the flow. And we know that that flow is staying the same. And because this boundary layer is really quite thin, dp is basically independent of y within the boundary layer. Okay. So dp independent of y in BL, right? We have dp dy is equal to 0. And we know dp dx is approximately equal to 0 because u infinity is not changing as a function of x. So then we can analyze this simpler form of the equations. So let's start to sub in our scales. We're going to have u infinity squared over L times u prime du prime dx prime plus vs u infinity over delta times v prime du prime dy prime. And that's going to be equal to nu, oops, why did I square that? Nu is not squared. Nu times u squared, not u infinity squared, right? Because we're taking a second derivative of u, but we're not taking, it's not squared in any way. So that's going to be u infinity over delta, which will be squared. And that's times di squared u prime dy prime squared. Okay, so again, we know that the order of all of these is going to be equal to 1, and we want to just find the scales. So we have order 1, order 1, order 1. Okay, what can we do? I would suggest that we take a look at VS, which we, how do I undo that? Which we have already solved for. So if we substitute VS into this expression, we're going to have u infinity delta over L times u infinity over delta. So the deltas are going to cancel, and the u infinities are going to be squared, and we're going to be dividing by L. So this is u infinity squared over L, which conveniently is going to match the coefficient from the other expression. So we can rewrite this whole equation. We could say we have u infinity squared over L times u prime di x prime plus v prime di y prime is equal to nu u infinity over delta squared di squared u prime di y prime squared. Okay, and we said this is order 1, but what about this? When you take something that's order 1 and you take something else that's order 1 and you add them together, basically it's still order 1. It's not going to be order 100. Maybe it's order 10 sometimes, right? But in general, if you take two things that are the same order of magnitude, you can assume that they're going to be of the same order of magnitude afterwards. So then we will say that those are both of order 1, and we can analyze the scales of the remaining variables. So we will say we have u infinity squared over L is proportional to nu times u infinity over delta squared. Let's multiply both sides by delta and divide both sides by u infinity squared. So if we have delta squared over L, it's proportional to nu over u infinity. What we can do is we can now divide both sides by delta. So we have delta squared over L squared is proportional to nu over u infinity L. And what I will notice about this at this point is that this is the same as 1 over the Reynolds number as a function of L, right? Because re L is equal to u infinity L over nu. So that's pretty convenient. What we can do now is we can say, take the square root of this. We have delta over L is of the order of 1 over the Reynolds number of L to the square root. Okay? And so this is the exact expression that we saw in the previous lectures. And like I said, if you were to do this Blasius solution approach, you would be able to get an exact result that matches that form, and you could actually calculate the coefficient. But in this case, we have done something much simpler than trying to solve ODEs or introduce scale or anything like that. I mean, you can do that. You can definitely do those solutions. But we did something very quick, very back of the hand, sketch out some important equations and identify important scales. And we can see how the boundary layer should grow. So we get a good sense of the physics of this flow field just by doing what we're calling scale analysis, and we'll take advantage of this later in the course as well. And so now what we're going to do going forward is we're going to simulate this flow, and we're going to use the tools that we've developed in this theory lecture to interpret that CFD result and to compare what we do numerically to some of the results that people have developed and empirically and analytically through experimentation and pencil and paper analysis like we've just done now. So that's all for the theory lecture.